In today's lesson, we'll be looking at the rules of probability.
As the party of adventurers ran from the group of monsters, they realized that there was a 60% chance the monsters contained a giant, 70% chance that the monsters contained an ogre, and a 40% chance that the horde contained both. What was the chance that the horde contained either a giant, an ogre, or both? Now, a probability function takes as input an event that might be true or false and returns a number from 0 up to 1 that gives the information about the truth of the event. Consider how to make this notion precise. An event is just any logical statement that can be assigned a probability. Let script f denote the collection of all events. The goal is to make script f the domain of our probability function. That is to say, the elements of script f will be the possible inputs to the probability function. It turns out that it will be helpful for script f to have several properties. First, any event that is always true will be assigned probability 1. Hence, the true event is in script sub f. Second, if an event is in script f, that means it's possible to assign a probability that the event is true. In turn, that means it should be possible to assign a probability that the event is false. If S is an element of script f, then the negation of S should also be an element of script f. The third and last property is a bit more unusual. So let's work through an example. Suppose that a fair coin with outcomes heads and tails is flipped over and over again, and S sub I is the event that the first I-1 flips were tails, and the ith flip of the coin was heads. So the first few coin flips were tails, tails, heads, tails, heads. Then S sub 1 and S sub 2 would be false, while S sub 3 would be true, S sub 4 would be false, S sub 5, S sub 6, all of those are going to be false. So the only S sub I which is true is the earliest head in the sequence. Now consider the logical statement S sub 1 or S sub 2 or S sub 3 or S sub 4, etc. That is the event that the first head occurred on the first flip or the second flip or the third flip, and so on. Given that each S sub I is assigned a probability, it would also be useful to guarantee that the logical or S sub 1 or S sub 2 or S sub 3, etc. was also an event. Therefore, our last property is that if there are a countable sequence of events, then the logical or of that sequence is also an event. If these three properties hold for the collection of events, call the collection a sigma algebra. So a non-empty set script f is a sigma algebra if for all sequences S sub 1, S sub 2, etc. of events in script f, we have the following three properties. First, the true statement is in the set, the negation of S1 is in the set, and S1 or S2 or S3, etc. is in the collection script sub f. Now that we have an idea of what kind of collection forms a set of events, it is possible to formally define what is a probability function. And there are two pieces to the definition of a probability function. For script f, a sigma algebra, P with domain script f and codomain the interval from 0 to 1. So all the inputs come from script f, all the outputs lie in 0, 1, is a probability function, also known as a probability measure, also known as a probability distribution, if the following properties hold. First, the probability of a true statement is 1. Second, countable additivity. If S sub 1, S sub 2, S sub 3, so on, are a disjoint sequence of events, then the probability that any one of those events occurs will equal the sum of the individual probabilities that the event occurs. So why make a formal definition of probability? Well, it turns out that many other rules that are useful in calculating probabilities can be derived just from the two rules given above. Here are 5 in particular. For any probability function P, and events S sub 1, S sub 2, S sub 3, etc., the following hold. First, the probability of a false statement is always 0. If S sub 1 up through S sub n are a finite set of disjoint events, then the probability that exactly one of those events occurs is the sum of the individual probabilities that the event occurs. The negation rule says that the probability of the negation of an event is 1 minus the probability of that event. The probability that either S sub 1 or S sub 2 occurs, and remember, for logical OR, both of those events might be true, is equal to the probability of S1 plus the probability of S2 minus the probability of both S1 and S2. And finally, if S sub 1 implies S sub 2, then the probability of S sub 1 is at most the probability of S2. Now, these 5 facts are actually all true for indicator functions as well. The fact that they hold for the generalization of probability functions, it's just icing on the cake. Now, to prove these facts about probability functions, it helps to do them in order. So let's start with the probability of a false statement is 0. Well, the probability of a false statement, false is the negation of true, so we know that false is an event. And let's just let that probability equal alpha. Then S sub 1 equals S sub 2, and so on, all equals false, form a sequence of events. And when you add up, as I goes from 1 to infinity, of the indicator of those events, you're adding up a bunch of zeros. So you get 0, which is at most 1, which means that the events are disjoint. That means we can apply countable additivity to say that the probability that at least one of those events occurs is the sum of the individual probabilities that one occurs. But we're going to bring out the probability of S1 and leave the rest of that sum for later. We can now use countable additivity in reverse to say that that is the probability of S1 plus the probability that at least one of S2, S3, and so on occurs. The chance that at least one of the events occurs, the chance that S1 occurs, the chance that any one from 2 up to infinity occurs, all of those are false because all of the S sub i's are false. So each of those probabilities is just alpha. So we have alpha equals alpha plus alpha, and so alpha equals 0. Now at this point you may be wondering, why not just assume that the probability that a false statement is 0 instead of trying to prove it? Well, there are 2 reasons. First, the goal in mathematics is to assume as few things as possible and then try to build out from there. Second, the more assumptions you make, the more likely you are to cause a contradiction in your assumptions, which brings the whole logical structure crashing down. So that is why the standard operating procedure in mathematics to assume as little as possible and see if we can get the things about probability that we wish were true as a logical conclusion from the few assumptions that we make about a probability function. Next comes the rule that for a finite set, S sub 1 through S sub n of disjoint events, the probability that at least one of the events is true is the sum of the probabilities that the individual events are true. Now here we're talking about a finite set of events. That's what makes us different from the countable sums that we had earlier. So let's start with any finite set of disjoint events, S sub 1 through S sub n, and let S sub n plus 1, S sub n plus 2, and so on all be false. So we're going to turn the finite set into a countable sequence by adding a bunch of false events to the end of it. Then the sum of the indicators of these events is the sum of the finite part plus the sum of the infinite part. Because the original n events were disjoint, we know that that first sum is at most 1. Because the rest of the events are all false, the infinite sum is then 0. And so we end up with at most 1 again. Therefore, the sequence is disjoint. So we can apply countable additivity. We can turn the probability of the countable logical OR of the events into the infinite sum of the events. We can break out the first n of those events. Then we can use the fact that all of those false events have probability 0 because we already proved that. And that tells us that the tail of those events is going to have probability 0. And so we're left with the countable logical OR of the SI is the countable logical OR of the first n with the countable logical OR of the rest. So really ends up being the countable logical OR just of the first n events. And that means that the probability of the logical OR of the first n events equals the probability of the logical OR of the entire sequence of events, which we've seen is just the sum of the probabilities of the first n events, and the proof is complete. Once we have this fact, the negation rule follows pretty easily. S and negation S are disjoint events because the indicator of S plus the indicator of the negation of S is 1, which is the indicator of true. So S and negation of S are disjoint events, and their logical OR is the true statement. So the previous rule tells us that the probability of S, or negation of S, is the probability of S plus the probability of negation S, which is the probability of a true statement, which by definition of a probability function will always be 1. And the proof just follows from rearranging the terms. Earlier, it was shown that for any two logical statements, the indicator of S or R is the indicator of S plus the indicator of R minus the indicator of S and R. And the same principle holds for events as well. This is called the principle of inclusion-exclusion. Now to verify it, a logical diagram called a Venn diagram can help to visualize what is happening. This diagram makes us aware that S or R is the disjoint logical OR of three parts. S and negation R, S and R, and the final part is negation of S and R. The left circle represents when S is true, while the right is when R is true. So S or R is the area of the two circles combined. Given events S and R, it turns out that SR and negation of S and R are disjoint. Also, logical OR equals R. Furthermore, S negation R and SR and negation SR are disjoint, and their logical OR is S or R. To prove this, we just show that the indicator of R is the indicator of R times the quantity, the indicator of S plus indicator of negation S, and use the rules of indicator and distribution of multiplication to say that that's the indicator of SR plus the indicator of negative SR. The left-hand side is 1, so the events on the right-hand side must be disjoint. And because the sum of their indicators gives the indicator on the left, their logical OR must equal the event on the left. The statement about the indicator of S or R is proved in a similar fashion. Now it is possible to show inclusion-exclusion for probabilities. We use the fact that S or R can be partitioned into S and not R, SR, and not S and R. We use the fact that negation of S and R and SR partition R, and S and negation R and SR partition S to get the final result. Now for implication, recall that S implies R means that whenever S is true, R must be true as well. And so if S implies R, that implies that SR is just equal to S. The diagram for implication is called an Euler diagram, and whenever S is true, R is true as well, so we indicate that by putting a circle for S completely inside a circle for R. Now, if S implies R, then intuitively R should be at least as likely to be true as S is, since whenever S is true, so is R. But there could be cases where S is false, but R is true. And the implication rule just makes that intuition precise. It says that if S implies R, that implies that the probability of S is less than or equal to the probability of R. So as before, we take our probability of R and we partition it into the two events where R happens but S does not, and the event where both R and S happen. This latter probability is just going to be the probability that S happens because S implies R. And so we see that probability of R is equal to some probability, which is non-negative, plus the probability of S, which means that the probability of R is greater than or equal to the probability of S. Now let's solve the story from the beginning of the lesson. Let's let S be the event that the group of monsters contains a giant, and R be the event that the group of monsters contains an ogre. Then, from our information from earlier, we're told that the probability of S is 60%, the probability of R is 70%, and the probability of both S and R is 40%. Which means that the probability that either S or R or both occurs is 0.6 plus 0.7 minus 0.4, or 90%.
So there you have it. With these rules of probability, you can break apart any probability problem into smaller parts that can be solved with knowledge of probabilities of the individual parts. See you later.